Okay, this is the asteroid collision problem. And the text goes as follows. Earthlings are attempting to slow an approaching asteroid so that over time it achieves a different orbit and doesn't smash into the Earth. To do so, they accelerate a 10,000 kilogram metal cylinder to a velocity of 10 kilometers a second away from the Earth. Okay, let's write that down before we keep reading. So we got a cylinder. Pardon my drawing, okay? And we're going to say that that has a velocity in this direction, 10 kilometers a second. And we smash it into an asteroid, okay? Oh, and let's write down that the mass of this cylinder is 10,000 kilograms. Okay. So to the right is away from the Earth. And we smash it into an asteroid which has a 5 kilometer per second velocity towards the Earth. All right. So there we are. And that's before the collision happens. Okay, so part A. If the Earthlings observe that after the collision, the two objects have merged into a single object and are moving toward the Earth at 4.5 kilometers per second, what is the mass of the asteroid? Okay, so in other words, they come together. So there's our asteroid, and the cylinder has smashed into it, and it's moving towards the Earth at 4.5. So this way, 4.5 kilometers per second. And we need to translate that into some mass and find the mass, or into some equations and find the mass of the asteroid. We'll call that m sub a. We want to know that for part A. Okay, well, this is a perfectly inelastic collision because they stick together and move as one afterwards. And that means that we can apply conservation of momentum. And m sub c is moving to the right. We'll call that positive, to the left negative. So its velocity before, we'll call, get my subscripts right here, C0 plus MA negative, right, because it's moving to the left, VA0. And that equals both masses moving together at this final velocity to the left, right? So negative V final. And let's define these things. So the initial velocity of the cylinder, 10 kilometers per second, magnitude-wise, VA0. So the initial velocity of the asteroid, its magnitude is 5 kilometers per second. And the magnitude of the final velocity is 4.5 kilometers per second. Note these are all magnitudes. I've already put in the directions in our conservation of momentum here. Okay, so if we're looking at this and we want to know m sub a, we need to isolate that on one side of the equation. So we'll start by leaving this one by itself over here. And we'll move the other one over. So that's going to be a plus this, if you distribute that minus sign through. And then we move everything else to the other side. Okay. So let's examine that for a moment. Make sure all our signs are A-OK, because if we miss one, oh boy, that would be unfortunate. Okay, so we just need to factor out MA over here. And we can actually do a similar thing over here. And then we divide both sides by this quantity. And that cancels it here and leaves us with a bunch of stuff that we can solve for, which is nice, okay? So if we go through it, mass of the cylinder is 10,000 kilograms. Velocity of the cylinder initially is 10,000 meters per second, so 10 kilometers a second. We add to that the final velocity magnitude, right? I've already put in the directions, don't put them in twice. And then you have the difference between these two things, these two speeds down below, and that will be that, all in standard units. If you plug all of that in, minus signs cancel, which is good because we're looking for mass here, and you get 290,000 kilograms. Ballpark, that makes sense. The reason I say that is because the thing only slowed down a little when we slammed this cylinder into it, so we would expect it to be much larger mass than the cylinder. Now, it does have a part B. Compare the impulse delivered to the cylinder by the asteroid to the impulse delivered to the asteroid by the cylinder. Explain your answer briefly in your written work, and remember that impulse is a vector. Okay, so we're a little out of space here, so let me stick part B up here. These will be equal in magnitude, opposite in direction. Remember that impulse is equal to the change in momentum of these things. And we're saying that momentum is conserved. So in other words, the change in momentum of the asteroid plus the change in momentum of the cylinder, remember these are vectors, has to equal 0, right? The whole system has to have a total change in momentum that is 0. So that means that these two impulses have to be equal in magnitude, but opposite in direction to one another, so that they total up to 0. Okay, I'll see you at the next problem.